When a bank approves a mortgage or a hospital flags a disease, the final call rarely comes from a human mind. It comes from mathematics. At the core of these systems is an algorithm. An algorithm is simply a repeatable set of instructions, essentially a mathematical recipe designed to process inputs into a specific output. For decades, software relied on traditional programming. Engineers manually wrote every explicit if-then rule. If a user clicks this button, then open this page. The computer strictly followed human orders. Machine learning completely flips that traditional process. Instead of writing the exact rules, engineers provide the computer with massive amounts of raw data and a desired final goal. The machine analyzes the data to derive the rules itself. By relying purely on the patterns it uncovers, the system acts intelligently without requiring human reasoning. If human engineers aren't writing the explicit steps, how does a machine know it is making the right choice? It relies on an objective function. An objective function is a mathematical metric that measures how far the AI's current guess is from the perfect answer. Think of this diagram like a topographical map, where the algorithm continuously probes the terrain to minimize its error and find the lowest possible point. Every seemingly intelligent behavior from an AI is the result of the algorithm blindly optimizing its internal math, trying to minimize its distance from that goal. To map out this data, an algorithm uses specific training methods. The first is supervised learning. Supervised learning is a technique where the algorithm is fed meticulously labeled data, like flashcards with answers on the back, to help it identify predefined patterns. Next is unsupervised learning. Unsupervised learning is when the algorithm is unleashed on massive datasets of unlabeled information to discover hidden clusters and relationships entirely on its own. Finally, there is reinforcement learning. Reinforcement learning is a process where the algorithm learns through trial and error within a specific environment to maximize a numerical reward. Regardless of the path taken, the algorithm is doing exactly one thing: converting real-world information into statistical relationships. This diagram shows a neural network making an initial prediction, a forward pass. The network takes inputs, the yellow circles, and multiplies them by internal weights to reach a first, often incorrect, guess. Weights determine the strength of connections between data points. Looking at the red calculation, we see how the algorithm finds the exact difference between its flawed prediction and the correct answer. To fix this, it uses backpropagation, a mechanism working backward from the error to adjust its internal variable weights. It repeats this loop millions of times using gradient descent. Gradient descent is an iterative optimization algorithm used to find the minimum of a function, continually pushing the error closer and closer to zero. By continuously adjusting those numerical weights, the machine is literally writing its own rules. It transforms random guesses into precise, reliable logic. The system processes probability and optimizes data. It does not comprehend the real-world context, history, or morality of the decisions it makes. Because it builds its rules entirely from historical human data, it mathematically inherits human prejudices. This results in algorithmic bias. Algorithmic bias occurs when a machine learning model produces systematically prejudiced results due to flawed historical data. In practice, this translates to predictive policing tools that disproportionately target minority neighborhoods, or financial lending models that penalize female applicants based on historical wage disparities. As these self-adjusted rules become infinitely more complex, we encounter the black box phenomenon. The black box phenomenon refers to AI systems where the internal decision-making processes are too dense for even their creators to trace or explain. This diagram maps out the consequences of that complexity. We have traded explainability for efficiency, creating an inescapable feedback loop where individuals lose privacy, organizations struggle with data quality, and society faces severe power imbalances, driven by systems that obscure their judgments. Treating algorithmic outputs as infallible, objective truths is a dangerous misconception. To ensure fair, transparent, and accountable systems, engineers must meticulously curate training data and design ethical, objective functions that account for real-world harm. An algorithm is merely a mathematical tool optimizing for a goal. Humanity is ultimately responsible for building the box and defining its rules.
AI isn't just another tool. It's an intelligence system for your dealership. Learn how at autoagentic.ai.
Or get your free copy of the Automotive Playbook for rebuilding organizations around AI. Also at autoagentic.ai.